Spectroscopy is the study of the interaction between matter and electromagnetic radiation. It is commonly used today and has numerous applications. Spectroscopy takes advantage of the fact that all atoms and molecules absorb light and emit light at certain wavelengths. To understand spectroscopy, one must first understand the structure of an atom. In 1913, Niels Bohr introduced his model of the atom, which includes a positive, dense nucleus consisting of protons and neutrons, surrounded by electrons in discrete orbits. Each orbit is associated with a specific amount of energy, and electrons can only be found at these orbits and not in between. This is because the energy of a bound electron is quantized, which means only a certain amount of energy can be absorbed or emitted at once. This amount of energy is associated with that atom's energy at different orbits. This absorption and emission of energy is how electrons go from one orbit to another. When an atom is in its ground state, all of its electrons are at the lowest orbital possible. To go up an orbital, an electron must absorb energy. With the absorption of energy, this electron becomes excited and moves to the next orbital up. However, it cannot stay there indefinitely, and this electron will soon go from the new orbital back down to the ground state. When you go from a high orbital to a lower orbital, energy is released. Energy is released in the form of a photon, which can be measured. The color of a photon is related to its wavelength, as seen in the electromagnetic spectrum. When this is the wavelength on this side, you can see that there's a very specific wavelength of the visible spectrum, and each color has its own corresponding wavelength. So if wavelength of the photon released is measured by its color, we can also get the energy of this photon released with the formula E equals hc over the wavelength. H and c are both constants, so if wavelength is known, energy that it released, that it took to go from a higher level to a lower level, can be known. Since each element and molecule has its own characteristic electron configuration, each element or molecule has its own characteristic emission spectrum. An emission spectrum is a picture, like these, that display at what wavelengths energy is emitted. This is the emission spectrum from hydrogen. So we can see that photons are emitted at these specific wavelengths, while for neon, photons are emitted at these wavelengths, shown by their colors.
Hi, I'm here with Varun, a graduate student in the Lee Lab. Would you mind telling us a little bit about your research?
Hi, I work in a neuroscience lab, and my main goal is to find all the molecular factors that come into play when there is changes in sensory experience in visual system.
So would you mind telling me a little bit about how you conduct the research?
So what I'm now interested in is a protein called MAP kinase, and I want to find out where it is expressed when there is a change in sensory experience. So what we do is we take the specimen that we're interested in and then stain with an antibody which is tagged to a fluorescent protein. So now we can find out that where this MAP kinase is present with this fluorescent tag.
So where does fluorescent spectroscopy come into play?
Right, so the next step for my research would be to actually locate this fluorescently tagged protein of interest in my specimen. For that, we use application of fluorescent spectroscopy, in which you can image minute details of a cell by using fluorescent microscopy. To do that, in this technique, what we do is that we irradiate the specimen with a particular wavelength of light, and our protein, which is fluorescently tagged, would emit visible light in return, in turn forming an image on our camera, which we can record and look at in our computers. So here's an example of one of my experiments in which my protein of interest is labeled by a green protein, which fluoresces green. Here is the neuron that it labels, and these are the other process of a dendrite. So now wherever there is green, the protein of interest is present. So now we can also take images of the whole specimen plane by plane and just play at it so that we can image the whole section and in a 3D structure, and sometimes can also make a huge 3D rendition of our image like that, where you can see particular spines and all other characteristics of the neurons and locate our protein of interest.
So as you can see, fluorescence spectroscopy plays a fundamental role in the research being conducted. Thank you for your time.